Hey everybody, welcome back. Today we're going to be doing a C++ program that does sorting through three different algorithms. We'll be using bubble sort, quick sort, and C++ standard library sort function. And the reason we're doing this is we're going to measure the performance of the algorithms behind it. I apologize if you hear thumping in the background. My upstairs neighbors are being kind of loud. So the way this program is generally designed is we have this broken up into four phases. So phase 1 and 2 is the implementation of the sorting algorithm. So we have bubble sort and quick sort, which are manually implemented, and the standard sort is using the C++ standard library. In phase 3, we're doing a setup where the random arrays are generated with different sizes. And then in phase 4, we have performance data collection, and this is where the program tests the sorting algorithms with four different array sizes. So we have 100, 1,000, 10,000, and 100,000. And then we're going to measure and record the time it takes for each of these algorithms to sort these arrays. So we'll do a quick summary of each of the functions. So the bubble sort implements the bubble sort algorithm. It repeatedly steps through the list, compares each adjacent element, and swaps them if the order is wrong. Then we have a partition function. This is a helper function for the quick sort, and it chooses a pivot and partitions the array around it. Then for the quick sort, we implement the quick sort algorithm. This uses the partition function to recursively sort the array. Then we have a function to generate a random array, and this creates a vector of a specified size. It fills it with random integers between 1 and 1,000,000. Then we're going to measure the sorting time. This is a template function to measure the execution time of the sorting function, and this uses a high-resolution clock to measure the time in milliseconds. And then finally, we orchestrate the entire program with the main function, and this generates the arrays of different sizes. It calls the sorting functions and measures their performance, and then outputs the results in a formatted table. When we run the program, immediately 100 and 1,000 pop out right away. The 10,000 size comes out about a little over 3 seconds later. These numbers are reported milliseconds. And then I'm going to speed this up about 15 times. And then the 100,000 size comes out at about 280 seconds, or a little over 4.5 minutes. So when I plotted this out in Excel, I took the data that was output, and you can see that the bubble sort took the longest amount of time, and that the quick sort and standard sort, the lines look flat because the amount of time that it took was minuscule compared to bubble sort. So then I took the quick sort and standard sort and I put them into the secondary axis just for comparative, to look at it comparatively. And the shape of the line then looks very similar because quick sort and standard sort were about the same size, although quick sort was a little bit more efficient. So if we wanted to summarize the performance differences overall, the bubble sort had the slowest algorithm for all the array sizes. The performance degrades dramatically as the array size increases, and for 100,000 elements, it took about a little over 4.5 minutes. Quick sort was significantly faster than bubble sort for all the sizes. It performed slightly better than the standard sort in this implementation, and then it scales well with increasing array sizes. And then the standard sort was very close in performance to the quick sort. It's slightly slower than quick sort in this case, but it's still very efficient, and it also scales very well with the increasing array size. Now when we look at the scalability, the bubble sort time increases quadratically with array size. So from 1,000 to 10,000, the time increased by over 100 times. And then when we look at the 10,000 to 100,000 element, the time increased by about 87 times. Now with quick sort and standard sort, the average time had much better scalability. So from 1,000 to 10,000 elements, the time increased by about 12 times for quick sort and about 13 times for standard sort. And then from 10,000 to 100,000 elements, the time increased by 12 times and 12.5 times respectively. So when we do a comparative analysis for all of these, the small arrays, say 100 elements, all the algorithms perform reasonably well. The bubble sort is only about 9 times slower than the others. For the medium arrays, 1,000 elements, the bubble sort becomes significantly slower by about 50 times than the others, and quicksort and standard sort still remain very close in their performance. And then when you start getting into the large arrays, 10,000 and 100,000 elements, bubble sort becomes pretty much impractical, and quicksort and standard sort maintain their efficiency, with quicksort showing a slight edge on performance. So practical implications for this: the bubble sort might be acceptable for very small data sets or educational purposes, but it's pretty much impractical for larger data sets. Quicksort demonstrates excellent performance and could be a good choice for custom implementations, and standard sort shows why it's often recommended for general use. It's highly optimized and performs very well across different sizes. So in conclusion, the data clearly demonstrates the superiority of quicksort and standard sort over bubble sort for all but the smallest arrays. So the choice between quicksort and standard sort would depend on specific requirements, but standard sort is generally recommended for its robustness and optimization across different scenarios. So that's about it. If you have any questions, leave a comment below, and I'll see you all next time.